Hello everyone. Today I will be presenting the paper Efficient Sequence Transduction by jointly predicting tokens and durations. This research comes from NVIDIA and Carnegie Mellon University, and it was published at ICML 2023. The paper introduces a novel architecture called the Token and Duration Transducer, or TDT. Its core claim is highly compelling. By making almost no changes to the existing model architecture, inference speed can be boosted by up to 2.82 times. This presentation will take about 15 minutes. At the end, I will also showcase my own Rust re-implementation called Melops, along with a live demo. Before diving in, let's quickly review the standard RNN transducer or RNNT architecture. It consists of three main components. First, the encoder processes the audio frames. Second, the decoder processes the text history. Third, the joint network combines both streams to output a probability distribution over the vocabulary, plus a special blank symbol. During training, we use the forward-backward algorithm to sum over all possible alignment paths. The most critical element here is that black symbol. It essentially tells the model, output nothing for this time step, and advance to the next audio frame. This design is exactly what allows LNNT to handle inputs and outputs of varying lengths. Where our NNT is powerful, it has a glaring performance bottleneck. During inference, our NNT must process the encoder's output frame by frame. Every single frame requires a call to the decoder and the joint network. However, in real-world speech, the ratio of audio frames to text token is roughly 7 to 1. This means that up to 85% of the time steps are just outputting blanks. The model is doing little useful work and purely wasting computational resource. If you look at the pseudocode on the right, the time index t only increments by 1 when a blank is predicted, and it can only move one step at a time. For a 1-minute audio clip, this can result in over 10,000 decoder calls, which is highly inefficient. TDT's core idea is incredibly intuitive. Since the blank symbol is just a way to skip a frame, why not just have every token explicitly tell the model how many frames to skip? On the left is the standard LNNT. It only advances by one frame when it sees a blank. In the middle is TDT. The model simultaneously outputs a duration, which we call D. Whether the model outputs an actual word or a blank, the time index t simply adds D. The design drastically reduces the required computational steps, directly translating to up to 2.82 times speed up. The most elegant part is that it requires absolutely little changes to the complex encoder or decoder structures. The architectural modifications for TDT are extremely minimal. We simply split the joint network's output vector into two parts. The first part is the token head. The first V dimensions predict the vocabulary. The second part is the duration head. The remaining dimensions predict the duration. Both heads apply their own independent softmax. They share the exact same joint network computation, so the parameter count barely increases. There is one key assumption here. The model assumes that the token and the duration are conditionally independent. Therefore, the joint probability can be neatly factored into the probability of the token multiplied by the probability of the duration. Experiments shows this assumption works perfectly and keeps both training and inference very clean. By introducing duration, the probability lattice calculations must be adjusted. This is the mathematical core of the paper. In a standard RNT, a node can only transition from its immediate left or bottom neighbors, but a TDT, a node can jump from a previous position t minus d. This gives the model the ability to make long-range jumps. For example, during a segment of silence, the model can simply predict a duration of 8 and instantly skip 8 audio frames. Finally, we calculate the total probability using a modified forward variable and define our loss function. Once we have the loss, we need to derive the gradient for training. A major contribution of this paper is deriving closed-form gradients rather than relying on automatic differentiation. This is because auto differentiation on transducer loss is notoriously slow. The paper also highlights 3 training checks. First, function merging. Computing gradients directly on pre-softmax logics to save messy computation. Second, logics under normalization, artificially shifting the probability distribution to encourage the model to predict longer durations. And third, loss sampling, mixing TDT and RNNT loss to prevent insertion errors during batched inference. Now let's look at the difference in inference algorithms. Left is RNNT, right is TDT. The difference is literally just 2 lines of code. TDT reads an additional duration index and the time steps update changes from hardcoded +1 to flexible plus duration. Most importantly, this time update is now unconditionally. Whether we output a word or a blank, we always take a massive step forward. This is the core reason why TDT drastically reduces decoder cost and accelerates inference. The experimental results are outstanding. On the English Libra speech dataset, TDT achieved a 2.19 times speed up, and the word error rate actually dropped slightly. The biggest speed up was on the German MLS dataset, hitting 2.82 times. This is because German subword tokens are typically longer, making frame skipping much more effective. The curve on the right also shows that as the maximum jump increases, the speed up increases. However, you hit diminishing returns around a duration of 6 to 8. On speech translation tasks, TDT isn't just faster, the quality actually improves. Blue scores increased by over 1 absolute point. This indicates that explicit duration modeling helps the model align audio and text better. Adding word reordering during translation. For spoken language understanding, TDT sets a new state-of-the-art record, while the speed up for SLU is smaller because the audio-to-text ratio in this text is much lower. The conclusion remains consistent. Across different tasks, TDT maintains or improves accuracy while delivering significant speeds up. This shall further explain exactly why TDT is so fast. As the maximum duration increases, the number of emitted blank spinball plummets, while the number of actual text tokens stays exactly the same. This proves that the model has learned a new behavior. It outputs normally during meaningful speech, and during silence or transitions, it simply uses long jumps to skip ahead. This validates our intuition. TDT successfully eliminates repetitive, meaningless computational steps. Beyond pure speed, TDT brings two unexpected benefits. First is robustness to noise. In noisy environments, TDT's error rate is significantly lower than our NNTs because the model simply learns to skip over noisy silent segments entirely. Second, it solves the repeated token problem. Standard LNTs often get stuck in infinity loops, like outputting 777 endlessly, which saturates the LSTM memory and prevents time from advancing. TDT's duration mechanism forcibly advances the time index, completely bypassing this shape and dropping the word error rate from over 60% down to 5.78%. We also need to compare TDT with another acceleration method called multi-blank transducer or MBT. MBT introduces large blank symbols for various lengths to skip frames, but the critical difference is that MBT can only skip frames when outputting a blank. When outputting a word, it still only advances by one. TDT, however, allows skipping on every step, regardless of the output. Experiments prove that at the same maximum duration setting, TDT's speedup is significantly better than MBT's. This proves that TDT's design allows text token to also carry duration is the superior approach. With the paper covered, I want to share my own implementation project, Melops. This is a CLI tool written in Rust, built to fully replicate TDT's high-efficiency inference. For the tech stack, I use Onyx runtime paired with Intel's OpenVINO backend. Running directly on an ARC-integrated GPU, I completely rewrote the TDT join logic from scratch in Rust without relying on the original Nemo framework. By integrating FFmpeg and YTDLP, it can download and transcribe YouTube videos natively. Running on an Intel Core Ultra 9 processor, the real-time factor hits 60. This means 1 minute of audio is processed in exactly 1 second. Here is a live demonstration of my implementation. The process is incredibly simple. Type the command in the terminal, pass a YouTube link, and the system handles the download and transcription. In this example, a 32-minute Berkeley CS61C lecture was completely transcribed in under 30 seconds. The transcription accuracy is phenomenal, accurately capturing technical jargon and names. This proves that TDT's efficiency isn't just theoretically data on an academic paper. It can be practically deployed in everyday tools on consumer hardware. To summarize, TDT's core contribution is achieving maximum efficiency gain with minimal architectural changes. It boosts inference speed by nearly 3 times, maintains or improves accuracy, and provides bonus resilience against noise and infinite loop. As demonstrated by Melops, TDT is highly suitable for deployment on consumer-grade hardware. And thank you for all your listening. I'm happy to take any question regarding the paper or the implementation details.